Okay, good morning. This is Vinayagamurthy from Midas IT. Today we will see the webinar on T-girder bridge, which is mainly into, we are looking after the modeling part of the T-girder bridge. Fine. Now, this is software page. I'll be opening a new window. I'm just save the file. Fine. So, as we know already, the icon is located in such a way, the modeling information, that is a node and element. Next is assign the properties, give the boundary condition, and then load, and then do the analysis and see the result and design. Now today's our main concern is to make a modeling things. So the first one, I'm creating the property for that. So it's a property, material, add, so add material, this is the database. I'm selecting a concrete material, so Eurocode C3037, and I can change the name concrete and click OK. And one more property I am selecting for steel, that is for your PSC cable properties, which is supposed to be a user defined property, because this is a high tensile wire, so we have to give the input according to the manufacturer manual input. Fine. And then section property, add, so as we already aware of this section property, first one is a database and user defined, value type sections. So this is the value type sections, and next is the PSC section. We have to give the input of the Prestress according to the reference picture. And here we are selecting the PSC T section. Is a PSC T shape. I'm giving the name as T girder. T girder. And here we have some selected database for that. Some cross section we can directly select, or otherwise we can select our user defined dimensions also. I will be suggesting to make your user-defined section. So I am making the cross section is none. As you know, you can select any cross section, they directly will get the properties. Instead of that, I am just making none. I am giving the dimension, and HL1 is 0.3, HL3 is 0.2, HL3 is 1 meter, BL1 0.2, BL2 0.001, and BL3 1.8, and BL4 is 2 meter. So this is my cross section. I'm just making the web thickness for shear and torsional calculation. I'm selecting automatic so that the program will calculate automatically what is the thickness for the web for shear and torsional. It is required. It is calculated from section property. Offset is center top. Now it is zero value. Once I calculate property, from the properties, it will calculate what is the required thickness for shear and torsional calculation. This will be calculated automatically. Okay, fine. So this is my girder 1. If you want to make some tapered section, also is possible from other sections. I will just show some different cross section, how we can easily modify the thing. I'm just worried the BL1 thickness is instead of 0.2, I'm making it 0.25. It is my T girder 2. Apply. So I can make the different cross sections. This is my tapered left section. Import from taper 2 to taper 1. That means the cross section which I have defined, there is a T girder 1 and 2. T girder 2, the web thickness is 0.3, T girder 1 is 0.25, and T girder 1 is 0.2. I am just showing what is the procedure to create the taper section. So I have selected the I and J then. This is what is showing here, size I and size J, which means for every element we have two ends. So the starting point while doing modeling, that is taking as the ith end, and right side is jth end. So from the existing property, we are selecting what is the cross section we are applying at the left side, what is the cross section at the right side. So in between it will make a tapering. And what kind of tapering? It is we have three types: linear type, parabolic, and cubic. Generally for this variation along the length it will be linear tapering. So I'm selecting linear tapering in Y and Z direction. And offset is center top, and click apply. Third section is added, and next section is taper right side. Here it is tapering from T girder 1, and J side is T girder 2. Apply. So it is added. And generally we will be connecting the diaphragms or cross beams to make connectivity between all the main girders. So I am making the diaphragm section or cross beam. It is solid rectangle. It's user defined type. I am making the height is 1.25 and B is 0.3. Again the offset is center top offset, Again, we have to detect the slab thickness. So I'm giving as a minus 0.5 from the extreme fiber so that the slab thickness on the T-B girder will be detected so that the cross beam or the diaphragm section will be placed below the slab. Now we can see the modeling how it is going to place. Let's see about that. This is my last section. I'm just clicking OK. So totally we have created 5 sections. That is a T girder. One that is thickness is 0.2 web thickness, and T girder 2 is 0.25. T girder left is tapering from T girder 2 to T girder 1. Taper right is T girder 1 to T girder 2. And the cross beam is a rectangle section which is placed below the slab. So material property, we already defined 2 properties. And the work we are seeing, this is the work. Generally this work will display in different color pattern. As you are seeing the material in section, it is showing in blue color. It means we have defined but not yet used. Why we have not used? Because the geometry is not yet created. Okay, fine. And now we will generate the geometry. That is a node and element. Create node. First node at the origin point. I'm copying 3 times, totally 4 girders, 3 plus 1. And we are copying in the y direction. It is a 4 meter. And apply. Now we are seeing the 4 nodes in the screen, and this is the node number which is displaying in the screen. So we are seeing 4 nodes in the model. And now we are going to create the girders. So girder, generally the modeling concept of any program, it is like just you have to make the connectivity between the 2 nodes. So we have to create the 2 nodes. Instead of that, we have the option to make quick modeling using extrude command. This extrude will help you to make the model quickly, and we have 3 types of extrusion. The node to line element, if you have a line, it will directly produce the node to line element. If you have a line to planar element, and planar to solid elements. Now we are going to make a line geometry. So this is the material, and this is the cross section. T girder 2. It is 5 meter, 1 time. Select all the members, apply. So this is the cross section which is applied. And next is your tapered left section. I am selecting these nodes, apply. Now we can see the cross section will be varying it. And then next is this set of nodes. This is my tapered one, 5 meter, maybe 2 times, applied. Again this set of node, we are using node to line element. So that's why I'm just selecting the nodes and selecting the material property and the cross section. 5 meter, 1 time, apply. Again the last node, this is my taper 2 and click OK. So this is the 25 meters girder, we created it. Okay. And this is a very wide cell. Now if you want to modify anything, for example, girders. And instead, if you want to make a 4 girder, just select it and just delete it. We can see only the 4 girders. Initially, I want to make a 4 girders only. To make your editing function, so I created 2 girders extra. Now we have 4 girders now. So editing is so simple. Now another thing is we have to connect the cross beams. So here I am using the create element option. This is my material and this is my cross section, that is a cross beams. I am just clicking on this member wherever I want to make the girder. And now you are seeing your the comments cross section are turned into black color. That means we have created and assigned to the model. If you want to cross check where you have applied it, just double click over there. This is the T girder 1, this is the T girder 2, this is the tapered right, this is the tapered left, this is the cross beams. And for the cross beams, this is the dimension we provided. I'm just reducing the dimensions 1 by 0.3. Now you can see it's flushed on the bottom. This is the T beams. And in general, we are connecting the slab to smooth load transfer from one member to another member. But in line geometry, we have a connectivity only at 3 locations. So because of that, we will be using dummy members to make to smooth load interface. So I'm creating one more property, that is your dummy property. How to make a dummy property in the software? This is the concrete property. I'm just copying it. This is the concrete. I'm modifying it. So I can just see the properties over here. I'm selecting ENRC, EN04, C3037. And here, this is the property of this material. Once I select the standard is none, and this property will be editable. Once the properties are editable, I can make weight density 0 so that the weight will not be calculated. So it is called dummy members. So I made only the weight density is 0. This name is dummy. So only the sectional stiffness will be there. There is no weight will be considered on this member. So this we are using to make the smooth interface between the 2 girders. Okay. I'm just selecting the dummy properties and connecting in the middle portion. Okay, fine. So now we can see the properties. This will be useful. I mean, the dummy members will be useful to make your grillage model. The grillage modeling concept is to make your smooth load transfer from one member to another member, which is the modeling wise, which is better than your single line geometry. Fine. So modeling is done. Next is a boundary condition. So boundary. For defining boundary, I have to copy the node to the bottom. So node and element, translate. -2 meter. I'm selecting the node is and the n nodes on both the sides. Yeah. It's copied over there. Yeah, and doing it one more time. Your actual depth, actually we are providing a support at both the ends, so it's simply supported. So I'm just acting only the edge node. So I can give the distance is -1.5. You can see this is exactly connecting at the bottom of the girder. And now provide the link between the support nodes and the structure nodes. We can see geometry. It is just a node at below the member, while seeing 3D view which is showing at the bottom. But in structurally it is not connected, so you have to make the connectivity boundary elastic link. When we are connecting the two nodes, we have to use elastic link type, which is asking the two nodes here. And also I can copy the link on the right side, which is 25 meter. We can see the elastic link over here. And we can check the distance between these two nodes, which is comes under 30 meters. I'm entering 30 meter. And these two nodes, I can directly click on the member, or otherwise I can type the node number also. So it's created the 4 links, and then your boundary, define support condition. The left side I'm translating translations of the directions, XYZ directions are fixed on the left side. And then apply. We can see the support condition by direction. This is support condition by direction, and the right side I'm selecting these 4 nodes and releasing the X direction, so that one end is spin and roller now. So this is the support condition, which is kind of denoting by the color notation. And the same thing you can see in support by direction also on the both sides. Already the legit link is connected. Now next thing is we have to apply the load. For defining the load, first we have to select the load cases, static load cases. Define the load cases like self-weight. Self-weight load type is dead load, add. Crash barrier load, it's dead load of component attachments. And next is a Prestress load. Load type is Prestress now. Fine. And then here how to apply the load one by one, let's see that. So this load self-weight is already, the load case is selected, and Z is vertical, so Z is -1. So that the program is calculating self-weight automatically and acting vertically downwards. That's why we are entering the factor is -1. And close the 3D view, and then your element beam load for cross barrier, eccentricity for cross barrier, because I want to apply the cross barrier load at the edge of the slab. So global y direction, it is 2 meter, and W is -2.5 kilonewton per meter. How to apply that? I'm selecting the reference at the exterior girder. Suppose this girder is my reference, so I'm giving 2 meter, apply. And then I'm selecting this is my reference element, and my eccentricity is -2 meter. You can see the load and see the 3D view. The load is applied at the edge of the slab on both sides. The thing is, we have to select the appropriate member for reference of this element beam load, because the load is always referring the element location. That's why we are given the eccentricity from the center line. So next is a Prestress load. Go to your load, temperature and Prestress. We have to define the tendon property. Define tendon property. First one is tendon property, next is tendon profile and tendon Prestress. So add, we are giving tendon property. I'm giving the name as tendon. We have 3 types of tensioning type, that is a pre-tension, post-tension and external prestressing. So generally these girders are post-tensioning methods, so I'm selecting post-tension. Material, I'm selecting the steel, which we have defined earlier. And total tendon area, here it is showing the standard strand diameters and the number of strands. Here this is strand diameters, I am selecting the 12.7 mm strands and 19 number of strands and click OK. This is the total tendon area of one cable. And diameter is 90 millimeter and relaxation coefficient as per the European standard. This is a high tensile wire, so we are selecting low relaxation. And the ultimate strength, yield strength, curvature friction factor, wobble friction factor are selected as per the standard, and anchorage slip is 6. I am just showing how to create, how I am creating the cable in Excel sheet. This make cable 1. This coordinates X, Y, Z. Zero, 1. For every 2 meter, we can calculate the distance. Center point is 15 because the total length is 30 meters. I am just calculating the value for half the length. Now we can see I just calculated the coordinates for half the length for 15 meter. Now just copying these coordinates, entering here. And selecting make symmetric tendon because it's calculated for 15 meter. Our actual girder length is 30 meters, so make symmetric. So it will be calculated for both sides, 15 meter. And starting your element number, which element you want to give a reference is my element number 1. So it's starting from element number 1 and then apply. So the coordinate it's calculated and apply on the member. Now you can see this is the first cable is created. And this is the cable profile on the member. And similarly, I can just copy this cable coordinate for other members also. Tendon profile, select, copy and move. I'm giving the this copy option. I can do it by two methods. So either I can give the element increment, or I can give equal distance also. I will show both the options. It will be easy to make it. Now you can see this is the tendon profile 2. So it is copied to second girder. The same way we can make several times. Again copy, this time increment is 2 so that our next girder it will make it for 3. And similarly say copy again 4 and then fourth girder it will make it applied. So totally I just copied 3 times, so totally I have 4 girder, 4 member, 4 pieces cable in the model. And this one is I copied 2 times. I'm just removing it and 1 copy and move, element increment is 4, applied. I can give a distance also 0, 6, 0. Okay, copy and move, element increment is 1, click OK. Now we have a 4 cables over there, and next step is the tendon Prestress. Go to tendon Prestress, this is the load case name we created earlier, and select all the 4 cables. It is got selected, and the input type is we can provide as a stress or a force. I'm selecting force type. This is a both-end jacking. I'm just giving the information like a both-end jacking now. Again, if you want to change the unit, you suppose if you know the values of the prestressing, it is just a ton force. I'm selecting ton force. You can give the force as 240 ton on both the sides. Grouting is after one stage. Add and OK. Now you can see we have applied the prestressing force. Now how to see that? Display geometry itself. Okay, and then next is the live load, mainly the live load part. Moving load, select the code, SLRFD, select the lane. Lane 1, eccentricity is 0 because I am selecting the members directly on the member. You can see, suppose this is my reference point where I want to create the lane, first lane, and apply. And similarly, I'm changing the lane to name. I'm removing the existing values in the table. I'm checking the next girder is the reference point and then apply. So we have created the 2 lanes. You can see in the geometry, it is a 2 lanes. The lane name also it is showing over there. I will just switch off this force value. Now you can see the lane 1 and lane 2 are displaying in the model. The next case is we have to select the vehicle. Add standard vehicle. SLRFD. So select the code HL93TRK and your dynamic load allowance 33%, so 32%. We can apply it over here itself and then apply. And one more vehicle is 93 TDM. Click OK and done. So now we have created the two lanes and we selected the two vehicles. And next is the moving load cases. So moving load cases is the last step for moving load analysis, because until this function in the tree menu, which will be displaying in blue color now. Add. Yeah. So this is the input table. I'm giving the lane, the load case name is MVC, moving load combination. We can select the loading effect by combined as well as independence. I'm selecting the combined option. So according to the structure and the conditions, we have to select the appropriate load effect. So I'm selecting it's the minimum load, minimum number of lanes to be loaded by 1, maximum is 2. So this is 93 TDM, selecting for lane 1 and lane 2. My first condition again. Second condition will be next vehicle, TRK vehicle, and again this can be loaded with minimum 1, maximum both the lane can be loaded, selecting both the lanes and click OK. So two conditions we have defined in the name of MBC, and click OK and close. Now these four loads are applied. This sulfate cross barrier load, this is a cross barrier load, and then the Prestress load, and this is the moving loads. And we can do the analysis, run the analysis. So the model is analyzed now. Now we are seeing the result. First thing is do the load combination, auto generation, select the standard and click OK. So this will generate the load combination for service stage and ultimate stage. And after that you can see the result. First one is the reaction. It will show the result for individual load cases as well as for the load combinations. We can select any load combinations or individual load cases. You can see the value and legend. Click OK. This is our reaction forces and the member for the particular load combinations. And next is the deformation. Deformation contour for the same load case. This is the deformed pattern. And how it is deforming? We can check for the animation also. Animate. Check how the structure is deforming. We can check the behavior in deformed position also. And next is the forces. Beam diagram. It is the bending moment. My component is the bending moment, and this is the bending moment values. We are seeing the bending moment diagram. And next is the FZ. FZ is nothing but the shear force, and Mx is the torsion. As this is a sulfate, so it is a grillage model. It is showing the torsional effect. And next is the stresses. Stresses for beam stresses. And this reference picture which is showing one component 1, 2, 3, 4. 1 and 2 are the top stress and 3 and 4 are the bottom stress. This is the stress values in the model. So, and also in the result table, we can extract the result in the form of tables. Go to result table, beam, forces, stresses, reactions, anything. You can select the load combinations or individual load cases. You can check the result in the form of tables. Again, these tables we can easily extract to Excel sheet. Just right click, you can see export to Excel sheet options. So select the location, it will export these values to the Excel sheet. So this is a modeling procedure and application of loads for a T-girder bridge. And the procedure is same for your I-girder composite also. This is just a modeling example. We are practicing today the modeling of T-girder bridge. Do you have any questions? Now you can ask your questions, please. Hello. Yes, I can hear you. You can ask the question now. Yes, sure. Actually, this is a recorded webinar. This is I already recording it, and I'll be sending the video link for the reference. In the meantime, you can practice this example on your side, and further, if you have any questions, we can discuss further. And this is just modeling information about the T-girder bridge. And the next webinar, I'll be organizing on the construction stage and the design of T-girders. Fine. So this this webinar I will send by email, and also again we will coordinate for the upcoming webinar for the design as well as the construction stage and for the and further new topics on the MEDA Civil. Fine. Thank you very much for joining us. This is Vinayagamurthy from MEDA IT. I will send the video to you. Yeah. Thank you very much. See you again. Bye.